Okay, yesterday we, let's say, starting from the classical Hamiltonian, including the behavior of n ions that are oscillating with respect to the equilibrium position, we made the hypothesis that the oscillation is small, so that can be considered to be just a perturbation to the static lattice approximation. And what we found is that the oscillations of the ions can be described by waves, elastic waves propagating through the solid. And there is a specific relationship between the frequency of those oscillations of those waves and the wave vector of the waves. We saw that the wave vector, the values of the wave vector come from the application of the Bohr-von-Karman boundary conditions. So in this case, let's say the problem of the oscillations can be discussed always in the let's say this is plus in the first Brillouin zone. And this is due to the fact that the dynamical matrix is periodical and has the same periodicity of the reciprocal lattice. So when we solve the eigenvalue problem, we know that the solution of this problem have exactly the same periodicity. So due to that, we expect to find omega, the values of the frequency that depends on the wave vector, and also on another index S. And the fact that we have an index S here comes from the fact that this matrix is a 3×3 matrix. So due to that, we have 3 eigenvectors and 3 eigenvalues for each value of k. So due to that, for each value of k within the first Brillouin zone, what we expect to find is 3 possible values for the frequency. We also know that due to the fact that into this matrix we have a sine square of k times r divided by 2, then d of k is equal to d of minus k. So the solutions are even due to the fact that the dynamical matrix is even with respect to the wave vector k. In this picture here, we plot omega as a function of the wave vector. So 1, 2, and 3 are the 3 possible values of the frequency. So this is, let's say, S equal to 1, S equal to 2, and S equal to 3. So the 3 parameters, 3 values of the frequency that correspond to a specific value of k. And those 3 values are related to the fact that we have 3 eigenvalues here that are the 3 eigenvalues for the related to that matrix. It's not said that the 3 values have to be different. So in principle, you may have that omega for a fixed k, omega 1, omega 2, and omega 3 are exactly the same value. So if you have an isotropic system, then in principle you may have that the 3 frequencies are the same. So this is just this picture with the 3 branches that are different with each other is to mark the fact that we have 3 different branches for each side, but in principle the 3 branches may be also superimposed and overlap. So you may have 3 values that are exactly the same. So you may have a degeneracy concerning the value of the frequency corresponding to a specific value of the wave vector. And regarding the 3 vectors E, so we have EKS. So for each k, we have 3 possible eigenvectors. Those 3 eigenvectors can be chosen to be orthogonal with each other. So in general, you suppose that the modulus of the vector is 1, and EK 1, 2, and 3 are again orthogonal with each other. And in general, it's possible to choose one of the three vectors so that that vector is parallel to k, so is parallel to the propagation direction, and the other two vectors are orthogonal to that. So we have one longitudinal mode and two transverse mode concerning the possible oscillations that you may observe within the lattice. And due to the fact that, again, here we have always in-phase oscillations. So if we suppose to consider the ions within the lattice, here I plot just a chain, but in general this is fine also for 3D. When we consider the amplitude of the propagating wave, then we have that if the displacement of this ion is described by this amplitude, then the displacement of the ion that is close to that in general is in the same direction. So you have in-phase oscillations. And due to that, you have that the frequency, the value of the frequency when the wave vector gets close to zero decreases down to zero. And we will see that this is quite important for what concerns the description of the properties of the solids, both for what concerns the specific heat and for what concerns the resistivity of the system, so the interaction with the electrons. All these results here are fine for a lattice where all the ions are equal with each other. So I assume that the mass of the ions is m, so the same mass for all the ions. So you have a lattice made of just one kind of atom here. But this is not the more general situation, because the more general situation is the one where you may have more than one kind of ion or more than one kind of atom within the lattice. So what happens in that case? I just give you the final solution, so I will not make all the calculations. So in this case, the idea is that if you have more than one ion per cell, then in place of finding this diagram, so if you have at least 2 atoms per unit cell, then what you have is that the problem is always symmetric. So you may always discuss the results within the first Brillouin zone. What you have is that you have the 3 branches here that we saw also for the previous problem. So for what concerns these 3 branches that are called acoustic, the acoustic branches, you have here, you have also here the acoustic branches. So in this case, you have exactly the same result, but you have also an additional, additional possible values for the frequency, and those values have a different dependence with respect to the wave vector, because you have additional 3 branches, and the structure of those branches is the following. So you have also, in this case, those should be symmetric with respect to k, and the main difference is due to the, let's say, due to the fact that while for acoustic branches you have, let's say, a maximum value here and then 0 as a minimum value, so the frequency of an acoustic branch moves from 0 up to a maximum value, that is this value here. In case you consider these 3 additional branches, you have those 3 branches have a frequency that ranges from a minimum value up to a maximum value, and both values are different from 0. Why do we have additional branches up here? Because, just to make an example, if you're supposed to have a situation like this one here, so let's suppose you have 2 ions per cell. So you have a lattice where you have ion, let's say A and B, A and B, A and B. So you have a cell that is made by a couple of ions. In this situation, there is a configuration that was not possible to obtain with the previous configuration, because if you are in this situation, so 1 ion per cell, we have seen that you may have just in-phase oscillations. But if you have 2 ions per cell, you may have an additional solution, and the additional solution is the following. That, for instance, ion A oscillates in this direction and ion B oscillates in this direction. So in this case, you have the opportunity to have a counterphase oscillation. Please consider that in this case, when you have the opportunity to observe this counterphase oscillation, even when the wavelength is infinite, let's say, or when k is equal to 0, because in this case, let's say, if you're supposed to have the, let's say, amplitude wave that propagates through the system, what you see here on the vertical axis is the amplitude of the counterphase oscillation. So the fact that here you have exactly the same value does not mean that they have to go both in the same direction. So if you consider the acoustic motion, then in that case they have to go exactly in the same direction in phase as it was for the ions in the previous situation. But if you consider these new additional branches, in that case, the amplitude that you read here is the amplitude of oscillation, but locally the oscillation is counterphase. So you have the opportunity to observe 2 kinds of motions, in phase and out of phase. So the important thing is that, as we saw for the previous situation, when you consider the in-phase oscillation, and the in-phase oscillation takes place with an infinite wavelength, then all the ions have to do exactly the same motion. So due to that, when you find a wave with the wave vector that is very small, then you have that the frequency goes to 0, because you have no stretching of the inter-ion forces if all the ions move exactly in phase in the same direction. But if you have the opposite situation, so if you consider a counterphase oscillations and all the ions do exactly the same motion, then in that case you have that locally within the cell you are stretching the spring that connects the ions, because they are performing a counterphase oscillation, and due to that they always stretch the, let's say, equivalent spring that connects, in this picture, ion A with ion B. So due to that, even when the frequency, even when the wave vector is close to 0, you have a value of the frequency here that is different from 0. So this is just due to the fact that you have the counterphase oscillations for those branches. And just to give you an idea of what is the name of those branches, in case you consider ion A and ion B, if ion A and ion B have a charge, let's say you have the, for instance, just supposed to have an ionic solid. In that case, the ions building up the system are, let's say, the system is globally neutral, but locally you have that one ion may have a positive, for instance, charge, and the other ion may have, for instance, a negative charge, as you have in sodium chloride, so in common salt. So in that case, if you have a counterphase oscillation, what is the effect? The effect is that the dipole moment of the cell changes because you change the distance between the two ions. If you change the dipole moment of the cell, or in general, if you change the dipole moment of your system, you have the opportunity to couple your system with the electromagnetic waves, because the change in dipole moment is one of the requirements for the coupling with the electromagnetic waves. And due to that, these branches are called optical branches. So in this case, you have optical branches, both optical branches and acoustical branches. In general, irrespective of the number of ions that you have in the cell, you always have 3 acoustic branches. So you always have those branches. The optical branches are found only if you have more than 1 atom per cell. So the optical branches are always in groups of 3, and the total number of optical branches is 3 times p minus 1, where p is the number of atoms in the cell. So if in your unit cell you have just 1 atom, 1 ion, then p minus 1 is 0. So you have 0 optical branches and 3 acoustical branches. If p is 2, then you have 3 optical and 3 acoustical branches, and so on. So the total number of branches is 3 plus 3 times p minus 1, so 3 times p. So that is the total number of branches, including both the acoustical ones and the optical ones. Okay. And please remember the fact that the acoustical branches have a frequency that is always larger than the acoustical ones. So an acoustic oscillation will always have a frequency that is larger than an acoustic one, even if the wave vector is the same. If you transform, let's say, if in your mind you transform frequency into energy, then this means that to build up an acoustic oscillation requires less energy than to build up to activate an optical oscillation. So in general, to activate an acoustic oscillation, less energy is needed with respect to the energy that you need to build up to start an acoustic one, an optical one. And for what concerns the energy consideration, so what is the amount of energy that is required to activate, for instance, an acoustic oscillation or an optical oscillation? Now I give you just an idea. Later on, I'll give you more details about that. In general, the energy of an acoustic or of an optical oscillation is of the order of tens of millieV. So let's say if we want to use on the vertical axis not frequency but energy, then the energy scale here ranges from a maximum of 10 millieV up to 40 or 50 millieV. So so those are energies that are smaller and smaller with respect to the, let's say, typical energies of the electrons that are of the order of the EVs. So this is to say that lattice oscillations are less energetic with respect to, in general, electrons, in particular the electrons that are close to the Fermi surface. Okay, so this is, let's say, the more general picture. Now let's go back to the previous picture, the picture that I used for the calculation. One thing that we may...
Professor?
Yeah?
Excuse me. In the order of magnitude of the energies of the optical branches is... I lost it, I'm sorry.
Let's say if on average this scale ranges from, let's say, 10 milli eV to 50 milli eV. So
Okay.
the full range of optical and acoustical oscillations is of the order of tens of milli eV. That
Okay.
depends on the solid one considers.
Okay, thank you.
You're welcome. And so I just recall here the plot of the yeah. So this is now let's go back to the situation that I used for the calculation. So in this case, we have just the acoustical branches, 3 frequency values for each value of K. And just a last comment, due to the fact that the value of the frequency comes from the solution of the eigenvalue problem, the frequency, so omega, or the square of omega, depends on lambda, the value of the eigenvalue. That depends on D. D includes the dynamical matrix, includes the matrix D of R, and the matrix D of R is the matrix that is defined as a function of the second derivative of the interaction potential between the ions that in the lattice that you are investigating. So the idea is that the frequency is related, the value of the frequency is related to the value of this second derivative. So that depends, this is just a qualitative comment. So I wanted just to stress the fact that the value of omega depends on the strength of the potential. So if in your lattice the interionic forces are not so strong, then you expect that this second derivative, let's say for the moment I give you relative indications. So my comparison is the stronger are the interionic forces. So the stiffer is your lattice, then the larger will be the value of the frequency. So in general, if the interionic forces are weak, then you expect to find a small value of the frequency corresponding, in this case, to the acoustic branches. If in your system the interionic forces are strong, then you expect to find a value for the frequency that is larger and larger with respect to the previous case. So in a very qualitative way, I wanted to relate build up this relationship between the actual value of the frequency and the stiffness of the crystal. So the stronger are the intraionic forces, the larger will be the value of the frequency. So for instance, if you consider the case, for instance, of diamond, where you have very, very strong interionic forces, then in that case, you have a value of the corresponding frequency that is very, very large with respect to a case of a typical metal. Later, we will make the comparison with the quantitative parameter, but for the moment, just keep in mind that what you have here on the vertical axis depends on the strength of the interionic forces. And you may, let's say, fix that or imagine that by recalling the what happens in the case of the spring mass system. So in that case, in the spring, in the case of the spring mass system, so you have your spring connected to a mass and you let this mass oscillate under the action of the spring, then the stronger, the larger is the value of the elastic constant of the spring, the larger is the frequency. So here, the more or less the point, you have a similar point. In this discussion, let's say that the second derivative of the interionic forces, of the interionic potential is in this picture the elastic constant of the spring. In fact, if you remember, the potential energy of the spring is 1/2 k delta x squared. So if you make the second derivative of that with respect to x, you have k. So again, this is just a very, very rough discussion, but it is to say the frequency is a consequence of the stiffness of the crystal. Okay. Now, one of the initial points concerning, one of the initial motivations that are behind this calculation is the one concerning the CV evaluation. So one of the things that were not explained using all the models that I presented to you up to now is how is it possible to evaluate, not how is it possible, but how is it possible to explain the actual dependence of the CV on temperature that you find in solids. So in solids, you find that the CV has a high temperature saturation value, and then at low temperature, you have a decrease, and then the CV goes to 0. So what we found for electrons is that at low temperature, CV actually goes to 0, but that dependence is linear. So you have a linear dependence of the specific heat due to electrons over temperature, and also the value that you find for electrons is lower and lower with respect to the experimental value that you find for solids. So the idea was maybe including the contribution of lattice oscillations, we are able to discuss and to find this dependence. So for the moment, what we know is that the motion of the lattice can be discussed in terms of normal modes of oscillation. So each value of k represents the wave vector of one, sorry, represents the wave vector of 3 normal modes of oscillation. So for each value of the wave vector, you have 3 possible normal modes of oscillation. So the idea is it possible to estimate the specific heat due to the presence of those normal modes of oscillation? again, just to make a very qualitative calculation that gives you the, say, in a small number of steps, the final value of the speed of the CV. The idea here is to evaluate the total energy of the system, in particular the, let's say, temperature dependence of the total energy of the system. What we know is that due to the lattice, if we just focus on the lattice, we have the static term, and the static term is 1/2 and sum over R of phi of phi of R, with R different from 0. But this term does not depend on the temperature. So due to that, we may, let's say, neglect this term because we have no T dependence. So this is, let's say, we may neglect that only because the specific heat is defined as the derivative with respect to temperature of the energy density. So due to that, I neglect all the terms that that do not depend on the temperature. So this is fine only in this picture. If your idea is to evaluate the total energy of the system, then you may not neglect this contribution. Then we have both the kinetic contribution and the potential contribution due to the normal modes of oscillation. How many normal modes do we have here at disposal? We have that the number of normal modes is proportional to the number of K values, and the number of K values is equal to the number of ions that we have in the lattice. Then for each wave vector, we have 3 modes of oscillation. So we have times 3. So this is due to the branches that we have in the system. Then each normal mode of oscillation includes a kinetic quadratic contribution and also a quadratic potential contribution, as you have in the mass spring system. So in that case, we have that the average energy per degree of freedom is 1/2 kBT times 2. So 1/2 kBT for each quadratic degree of freedom. In this case, we have 2 of them for each normal mode of oscillation. So we may simplify those two, and at the end, we have 3n kBT. And in this picture, if you make the derivative of the specific heat, if you make the derivative of the total energy with respect to temperature, then you divide by the volume and you write n as number of moles times the Avogadro number. What you find is that in this situation, the CV is 3n times the constant of gases. So, and this is equal to the, let's say, high temperature saturation value that we have here. But in this condition, we have no possibility. There's no possibility to have any temperature dependence of the value. So at this point, even if we have included the possibility for the ions to oscillate, then the oscillation is not enough to describe this low temperature behavior. So what is the, I anticipate one thing, what is the mistake in this calculation? In this calculation, I made a mistake that is not let's say, is not a mathematical mistake, or I hope so. But in this case, the mistake is concerning this factor here. Because while evaluating the total energy of the system, I multiply the energy, the thermal energy corresponding to one normal mode of oscillation by the total number of oscillation modes that I have in the system, without considering that maybe, depending on the energy, not all of those normal modes may be active in the system. just to make an example, again, I'm making an anticipation. In this picture, one classically expects that if you have normal modes of oscillations, then all of those normal modes of oscillations will be in the system. But it may happen that, for instance, if you're at low temperature, not all the normal modes are active in the system. But to discuss the problem in these terms, we have to switch from a classical representation of the normal mode of oscillation to a quantum mechanical representation, as you did for the, let's say, quantum mechanical oscillator. So in that case, when you switch from the spring mass representation to the quantum mechanical, quantum mechanical harmonic oscillator, you see that you may have different energy levels, and those energy levels may be or may not be excited, depending also on the conditions where the system is found. So in general, the mistake in this calculation is to include here the total number of normal modes of oscillation. So when they saw this point, the idea was, okay, we have found the presence of those normal modes of oscillation, so we have a clear description of how the oscillations within the solid may take place. But at this point, we have to switch to a, let's say, quantum mechanical representation of the problem, so to introduce the possibility that not all the modes in the system are active, or to include the fact that the behavior of those normal modes of oscillations may be not classical, but described by quantum mechanics. So the next step is, let's try to, let's say, take into consideration this point of view. So let's try to move from the classical representation to the quantum mechanical one of this problem. And let's say, since the calculation is not long, I may split that in two parts. So in case that takes too much time, then I make the break into that. So the starting point is to recall to make this operation, the starting point is to remember the initial Hamiltonian. So this was the, let's say, then I have U0, that is the equilibrium term. Then I have 1/2 sum over R and R prime with R different from R prime of U of R d of R minus R prime U of R prime. So this was the initial expression for the Hamiltonian, and in that case, P was the momentum of the ion in position R, and U is the displacement of the ion in position R. If we, let's say, at this point, U is just the amplitude in this picture. U is just the amplitude of the oscillation field that is evaluated in position R, and U of R prime is the amplitude of the oscillation field evaluated in position R prime. In this case, we may do an operation, let's say, we may transform, we may consider U and P. Here, U and P are conjugated variables. In this, we may consider U and P as operators, as is done in quantum mechanics when you write out the Hamiltonian of the system. So U of R, as U in principle was a field, is the oscillation field. In this case, you may consider U of R an operator that tells you what is the amplitude, then when applied to the actual amplitude of the system, tells you what is the amplitude that you have in the system at a specific position. So in this case, U of R and P of R can be interpreted as operators, as again was done in the when you first make the quantization. So when you apply the Schrödinger equation, you have both the kinetic operator and the position operator. In this case, you have both the kinetic operator, momentum operator, and the not positions, but the amplitude operator. And another important thing is that we know that if we switch to the coordinate representation, to the wave vector representation, we have a problem that may become diagonal, because we know that if we introduce plane waves in the system, and if we solve this eigenvalue problem, so if we solve this eigenvalue problem, we know that the dynamical matrix can be diagonalized. So the problem is diagonal in the wave vector space. So the idea is to, let's say, rewrite this Hamiltonian, considering U of R to be an operator, and using the representation of those operators not in the coordinate space as we have here, but in the wave vector space. So just a moment that I yeah, so if we consider the U of R can be expressed in terms of the oscillation vectors. So we know that the arbitrary expression for the oscillation can be done in terms of the polarization vectors of the different oscillations. Then we include the phase term, and in this case, we need also an amplitude. So in this case, we may write U of R as a combination of oscillations, and the oscillations are described. So we use we make a discrete Fourier transform. So we have the phase where we insert a possible wave vector that belongs to the first Brillouin zone. Then we have the polarization vector. So we make a combination of all the possible oscillations that we may have in the system. And for each of those oscillations, we include also the opportunity to have an amplitude. In this case, if U of R is the operator that tells you what is the amplitude of the oscillation corresponding to coordinate R, the equivalent of that in the Fourier representation is Q, because Q tells you what is the amplitude of the normal mode that is indexed by K and S. So the two operators that we have here are U of R on one side and QKS on the other side. And in this picture, there is also a normalization factor that is given by the square root of N. And we may use exactly the same expression for P. In this case, we have PKS, EKS, e to the I K times R divided by the square root of N. And one last thing then I will recall at the end of the calculation, if we consider U, but the same result is fine also for P. In general, if you remember, when you introduce the position operator, momentum operator, those operators has to be self-adjoint, because those operators correspond to observable quantities that you may want to measure in the system. So here we have the same requirement. So U of R and P of R has to be self-adjoint operators. So if we make the adjoint of U of R, then we have the sum of K, and we want that this has to be equal to U of R. So we want the operator U, and the same is fine for P, to be self-adjoint. So in this case, we have QKS, the adjoint, EKS, e to the minus ik times r divided by the square root of n. Then here we, let's say, we have a phase with a negative sign here, and here we have a phase with the positive sign. So in principle, if we change the index of summation from k to minus k, so if I switch from k to minus k, then this becomes equal to sum over k and s of q cross minus ks e minus ks e to the I k r divided by the square root of n. If you remember, the problem that was solved using the dynamical matrix is even. So if you have E of minus k, that is equal to E of plus k. So in this case, I may write here plus k, because minus k and plus k in this situation give you exactly the same vector. Then we have here in this expression q cross minus ks. In the other expression, we have qks. So for U to be self-adjoint, we have that qks has to be equal to q cross minus ks. And this will be one thing that I will use at the end of the calculation. So we have this relationship between the operator in the wave vector space, and the same condition holds for P, because if you make exactly the same steps of the calculation, you find that PKS has to be equal to P cross minus KS. So this is just a condition due to the fact that both the amplitude operator and the momentum operator has to be self-adjoint. And yeah, since let's say if for you is fine, since now is exactly 10 o'clock, then I needed this part to, let's say, set up the calculation. So now to start with the calculation, I will just substitute this expression for U and this expression for P within this Hamiltonian, and I will see what happens when you make the calculation. So for me, it would be better to stop here, and then in the second part of the lesson, we have time to make the full calculation and to make comments on that. Okay, so now I stop the registration, and after the break, I go on with the details of the calculation